You're trapped on a slow network, just staring at that spinning wheel, waiting for an application to download like a mountain of data. The interface is completely grayed out and you
Yeah.
can't click a single thing. I mean, we've all been there, right?
Oh, yeah, absolutely. It is just the worst feeling.
Right. But what if I told you that the very same web browser you're using right now currently has the power to, well, commandeer like 50% of your computer's hard drive space?
Wait, 50%?
Yeah, 50%. It can completely bypass the network and run these massive data operations locally. The idea that web applications are restricted to this tiny, like, 5 megabyte storage limit is a complete myth.
It really is. And the
Mhm.
shift we're talking about today, it fundamentally changes application architecture.
Exactly. So our mission for this deep dive is to explore the mechanics of how modern web apps can store and process gigabytes of data directly on your machine and do it without freezing the interface for even a millisecond.
Right, which is no small feat.
Not at all. And we're pulling our insights today from a deeply technical breakdown by software engineer and tech writer Aaron Rose. It was published on tech-reader.blog, and it's titled The Secret Life of JavaScript, IndexedDB.
It's a fantastic piece because for years, developers have treated browser storage like a Post-it note stuck to your monitor,
Yeah, like just saving a dark mode preference or something.
Exactly, or a temporary session token. But Aaron's piece looks at what happens when you realize there is a fully staffed, enterprise-grade filing department operating silently inside your desk drawer that you never even knew was there.
I love that. And to frame this, think about most websites like fishbowls. They can only hold a tiny amount of data locally. But what we are talking about today is turning that fishbowl into a massive deep sea aquarium.
That is a perfect way to look at it.
So to really understand how developers are making this shift, we're going to step into a specific scenario that Aaron sets up in his post. He introduces us to Margaret, who is a senior software engineer, and Timothy, her junior colleague.
Right, and they aren't in your typical, neon-lit startup office with beanbag chairs.
No, not at all. Aaron places them in this grand, quiet Victorian library in London.
Which is such a great stylistic choice, right? The setting immediately signals that we're talking about real software craftsmanship here.
Exactly. We aren't just hacking together a quick landing page. We're engineering robust, data-heavy software where code quality is the unspoken objective.
Right, and in the middle of this beautiful library, Timothy is staring at his screen, just watching a red error bloom across his console.
Oh man, the dreaded red text. What does it say?
It says, uncaught DOM exception. Failed to execute set item on storage. Setting the value of username exceeded the quota.
Ah, the classic quota exceeded error.
Yep. It happens the exact millisecond you try to shove 5.1 megabytes of data into local storage.
So what exactly is Timothy trying to build that's causing this?
Well, he's building an application with a highly optimized infinite scroll feature, and it's backed by a streaming data engine.
Okay, sounds pretty standard for a modern app.
It is, and it works flawlessly on the first load. But the problem is, every time the user hits refresh, the application drops the local state.
Yeah.
So it has to pull 100,000 diagnostic records across the network all over again.
Wow. Which is obviously terrible for the user experience and honestly, terrible for server costs too.
Exactly.
Yeah.
So Timothy does the logical thing. He tries to cache those 100,000 parsed log records locally using local storage so they persist between sessions.
Right, that makes sense on paper.
It does. But the moment his data set hits that 5 megabyte threshold, the whole system just violently crashes.
Okay, but I have to push back on this a little bit because if you think about it, 100,000 records of standard diagnostic text, that doesn't actually sound like a massive payload in today's world.
No, it really doesn't.
Right. Like if I download a CSV with 100,000 rows, I'm looking at maybe a few megabytes. So why did simply caching a standard data array crash his entire application so violently?
Well, that's the thing. It's the execution mechanism, not just the file size. Margaret looks at Timothy's failing code and points out the critical flaw. She calls it the string trap.
The string trap. Okay, what is that?
So Timothy isn't just saving raw data. He's taking a massive array of really complex JavaScript objects and forcing them through a function called json.stringify.
Oh, because local storage can't hold complex objects? Or...
Exactly. It cannot hold raw arrays or JavaScript objects. It only accepts raw synchronous strings.
Okay, let's unpack this. Because stringifying a 5 megabyte array sounds pretty trivial for a modern CPU. But in the context of a browser, it's a structural bottleneck.
It's a huge bottleneck. What's fascinating here is the violent friction between an asynchronous data pipeline and a synchronous storage API.
Right, because those two things just do not mix well.
They don't. Timothy is pulling down this data using an NDJSON stream. That stands for New Line Delimited JSON.
And the beauty of NDJSON is that it streams in asynchronously, right?
Exactly. The browser can process it line by line in the background. So while that's happening, the user can continue to interact with the page smoothly.
But to save it into local storage, he has to change that entire approach.
Yes. He has to accumulate all those individual lines into one giant array in the system's RAM. And then he has to run JSON.stringify on that entire massive block of data all at once.
And because local storage operations are strictly synchronous, that stringification process completely blocks the main thread.
It completely blocks it.
It's like stopping rush hour traffic on a major highway just to force every single driver to roll down their window and sign a physical guest book.
That's a great analogy.
Right. Like the cars are the data packets and you had them moving smoothly at 65 miles per hour, but by forcing them through this tiny single file synchronous checkpoint, you create a miles-long backup. Everything just freezes.
Yeah, the UI completely locks up.
Yeah.
Because JavaScript is single-threaded.
Right. It can only do one thing at a time.
Exactly. So while the browser is spending precious hundreds of milliseconds marshalling memory to convert 100,000 complex objects into one gargantuan string.
Just to write that string to the disk synchronously.
Yes, the browser literally cannot do anything else. Hover effects stop working. Clicks are completely ignored. The page basically feels dead to the user.
And doesn't that massive memory spike cause other issues too?
Oh, absolutely. It triggers the browser's garbage collector to aggressively step in immediately afterward. It has to clean up all that discarded object data from the conversion, which causes even more stuttering.
Wow. And Margaret captures this perfectly in the piece, right? She reprimands Timothy by telling him he's treating the browser like a basic cookie jar when he should be treating it like a production database server.
Yes, local storage is the cookie jar. I mean, it was engineered over a decade ago for tiny session IDs and little strings. It was fundamentally never designed to act as a data warehousing layer.
Which leaves Timothy in a really difficult spot. The cookie jar is useless for this kind of scale, but his core engineering requirement is still there.
Right. The diagnostic data must survive a page refresh without incurring a massive network penalty.
So if local storage crashes the main thread, the browser actually has a built-in escape hatch for this exact problem. And this is where Margaret steps up to the whiteboard in the library and writes a single command.
IndexedDB.open.
IndexedDB. So this is the production database Margaret was referring to.
Exactly. It operates entirely differently from local storage at the architectural level.
Right.
First of all, it just doesn't care about strings. You don't ever use JSON.stringify.
Wait, really? So how does it store the data?
It relies on the structured clone algorithm that's built natively into the browser engine. This means you can handle complex, nested JavaScript objects, or raw binary blobs, or even cryptography keys.
And it just takes them.
Yep, it stores them exactly as they are, natively.
So no more forcing cars to sign the guest book. You bypass the stringification bottleneck entirely, which I imagine immediately flattens out that massive memory spike in your RAM.
It completely flattens it out.
But it's also transactional, right? Like, if you are writing 100,000 records and the user accidentally closes the tab at record 50,000, a normal write process might leave you with corrupted, half-written data.
Right, which is a nightmare to debug.
But IndexedDB rolls back the transaction. It maintains database integrity with the same rigor as a back-end SQL server.
It really does. It provides full ACD-compliant transactions directly on the client side.
That's incredible.
But the defining feature here, the thing that actually solves Timothy's problem, is that IndexedDB is entirely asynchronous.
Ah, so it doesn't block the main thread.
Exactly. Database reads and writes happen off the main thread. You can push gigabytes of data into this database, and the user can still scroll a 60 frames per second animation without dropping a single frame.
So what does this all mean for the user? I mean, we talked about the 5 megabyte quota of the cookie jar, but if IndexedDB scales up to requisition 50% or more of your free hard drive space?
Which it can, easily.
How does that change the paradigm of what a website actually is? Like, if I have 100 gigabytes of free space on my laptop, a single web application can silently claim 50 gigabytes to store high-resolution 3D mapping data or a full offline music library.
Or in Timothy's case, an endless ocean of diagnostic logs.
Right. It just completely changes the game.
It really erases the boundary between a native desktop application and a browser-based application. When developers leverage this storage quota properly, They stop treating the browser as just a dumb document viewer.
And they start treating it as a localized operating system.
Exactly. But, knowing that this massive asynchronous vault exists is only half the battle. As Aaron highlights with that Victorian library setting, real craftsmanship isn't just about selecting the right tool.
Right, it's about the elegance of the implementation.
Yes, because native IndexedDB is famously difficult to work with.
Yeah, I've heard developers really struggle with it. Why is that?
It relies on a very old event-driven API model. You have to constantly set up event listeners for on-success or on-error callbacks.
Oh, and that leads to callback hell, doesn't it?
It does. It quickly leads to deeply nested, completely unreadable code. If Timothy just raw dogs the native IndexedDB API, he's going to end up with a brittle, unmaintainable mess.
Precisely. So Timothy has to design an architecture that bridges his modern NDJSON network stream with this slightly archaic database API.
And he does this through what Aaron calls a streaming marriage.
Streaming marriage, I like that.
Yeah. Timothy realizes that because he is using an NDJSON stream, the network is handing him the diagnostic records one chunk at a time, sequentially.
So he doesn't need to wait for all 100,000 records to arrive before he starts writing them to disk.
Exactly. He doesn't have to wait.
Here's where it gets really interesting. Timothy integrates the database writer directly into his response stream reader. He essentially pipes the network stream directly into the database transaction.
It is an incredibly sophisticated data pipeline. Timothy wraps that clunky, event-driven IndexedDB boilerplate into a clean, promise-based utility.
And by using promises, he can utilize modern async await syntax, right?
Yes. This allows him to open a transaction, read a chunk of JSON from the network stream, parse it into an object, and then just await the database insertion before moving to the very next chunk in the stream.
Okay, let's visualize this memory footprint using a warehouse analogy, because caching with local storage was like waiting for a massive freight train to deliver 100,000 boxes.
Right, all at once.
Yeah, and stacking every single box in the middle of the warehouse floor, which represents your system's RAM, and then trying to shove them all onto a single shelf at exactly the same time.
And the floor just collapses under the weight.
Exactly.
Yeah.
But with this streaming marriage, Timothy is standing next to a moving conveyor belt. As the network delivers one box, he grabs it, walks it over to the IndexedDB shelf, slides it into place, and then turns around for the next box.
And because he is processing one box at a time, the warehouse floor, the browser's memory heap, remains completely empty.
So the garbage collector never has to panic.
Exactly, because there is no massive accumulation of objects sitting in memory. The data simply flows from the network interface through the parser, and straight down into the physical disk storage.
And since IndexedDB is completely synchronous, the main thread isn't involved in the heavy lifting at all. The user interface remains perfectly fluid.
It's brilliant. But this does raise an important question about lifecycle management.
Oh. What kind of lifecycle issues?
Well, IndexedDB transactions have this quirk where they automatically commit and close if they sense inactivity on the microtask queue.
Wait, so if your network stream pauses for just a second because you have a slow connection?
The database might assume you're completely finished and prematurely close the transaction.
Oh, wow. So Timothy has to maintain this delicate balance. He has to keep the database transaction alive while waiting for the network stream to yield the next chunk of data.
Which is exactly why wrapping it in promises is so crucial. It gives him explicit control over the flow of execution and error handling.
Ah, I see. So if the network stream fails halfway through, the promise just rejects.
Exactly. The promise rejects, the database transaction aborts, and the system rolls back to a clean state automatically.
No corrupted data left behind.
Not at all. It is the highest level of software craftsmanship. He has essentially built a fault-tolerant, low-memory, asynchronous data pipeline right inside a web browser.
So let's look at the payoff of this architecture. Timothy finalizes his promise-based pipeline. He saves his files, and he completely clears his browser cache to simulate a brand new user session.
Right, a totally fresh start.
And then he triggers the application. What happens?
The network tab lights up immediately. The NDJSON stream begins delivering chunks of data. But this time, the application doesn't build a massive array in memory.
It bypasses the local storage cookie jar entirely.
Entirely. It takes each JavaScript object as it arrives and writes it silently into the IndexedDB database. So Timothy opens the browser's developer tools, he navigates to the application tab, and he expands the IndexedDB tree.
And what does he see?
There it is. A beautifully structured, highly indexed table containing tens of thousands of raw diagnostic records.
And the memory usage just stays totally flat during all this.
Completely flat. The UI doesn't stutter even once.
But the true magic of this architecture reveals itself when he tests the initial problem, right? He hits the refresh button on the browser.
And instantly, the infinite scroll grid on the screen populates with data. I mean, instantly.
Zero network latency.
Zero. Because the application intercepted the request and queried the local database instead. It didn't even bother hitting the external server.
That is wild. The data is just retrieved from the local hard drive in a fraction of a second.
Exactly. No spinning wheel.
No grayed out interface. No waiting for a server halfway across the world to send back data that you literally already downloaded 5 minutes ago.
If we connect this to the bigger picture, Timothy didn't just patch a simple memory leak here. By combining the Streams API with a transactional client-side database, he completely dismantled that 5-megabyte wall that limits how most developers think about the web.
He really did.
He built an offline-capable, gigabyte-scale data architecture that operates entirely on the user's local machine, but with the performance profile of a native installed application.
It fundamentally shifts how we view the relationship between the client and the server, which, leaves you with a thought really worth unpacking.
Yeah.
We are so accustomed to the idea that the cloud is the ultimate destination for all heavy computing and storage, right? Like our browsers are just these thin glass windows looking into that distant server.
Right, just a dumb terminal, basically.
Exactly. But if web browsers can now natively act as massive gigabyte-scale offline databases, utilizing up to half of your machine's actual hardware to run these complex data pipelines, at what point does the reliance on the cloud become a choice rather than a necessity?
That is a fascinating question.
Are we quietly returning to an era where the internet is no longer a destination you constantly query, but simply an invisible delivery mechanism for heavy, powerful applications that run entirely and privately on your own machine? Think about that next time you assume a web app can't handle real data.